I will teach you about some ways to prepare alkenes, the halogenation of alkenes, and how to form halohydrins. In Chapter 8, you're going to learn how to transform an alkene starting material into a diversity of products. In this video, we're going to focus on the halohydrin and the 1,2-dihalide products. But in subsequent videos, you'll learn how to convert an alkene to an alcohol, an alkane, a 1,2-diol, a carbonyl compound, a cyclopropane, an epoxide, and you've actually already learned how to convert it to a halide. So how are alkenes prepared? We're going to talk about this more in a subsequent chapter, but essentially it's the reverse of the addition reaction you've already learned, and it's called an elimination. So you have something like this bromocyclohexane, and in the presence of strong base, you eliminate HBr to form a double bond. I'll teach you the mechanism for this in a subsequent chapter. We could also start with an alcohol and eliminate water in a dehydration reaction to get an alkene. And you'll also learn this in a subsequent chapter. Halogenation. First of all, this is only going to work with chlorine and bromine. Iodine doesn't work well, and fluorine is too violent of a reaction for it to be useful. In fact, fluorine is so dangerous to work with that almost no one works with it. So what's happening in this reaction? We start with a double bond. That goes away. We now have a single bond between those two carbons. And we have two bromines. So we've created two new carbon-bromine bonds, and we've gotten rid of the pi bond. And notice we have two products, and these would be enantiomers. And notice that both of the products are trans. The bromines are on opposite sides of the cyclopentane ring. The bromine molecule is nonpolar but polarizable, meaning its electron density can shift and move. And an approach of a nucleophile will induce a transient dipole. So as the nucleophile approaches, it can cause one end of the bromine to have a slight positive charge and the other to have a slight negative charge. So you can think of bromine as a bromine atom bonded to a good leaving group. Now, based on what we saw with the addition of HBr or HCl to an alkene, you might think that this is how the reaction works, where the nucleophile is the alkene, it attacks the positive end of the bromine, kicking off the other bromide, and then you would yield a carbocation intermediate. However, while part of that is true, the alkene is the nucleophile attacking the bromine, it's not all true, and I'm going to explain why in a minute. But let me direct your attention to this picture. So this is a picture of bromine. It's this deep burgundy color, and it's very, very dense. It's a very, very dense liquid. And it's somewhat dangerous to use. So later I'll show you some alternative reagents that can be used instead of bromine. Now in the previous slide, I showed you a carbocation. However, if a carbocation really was produced in the mechanism, we should get both syn and anti-addition, because the bromide that attacks could attack from the top or from the bottom. But we don't see that. We only see anti-addition to give the trans product. So syn addition would give a cis product, anti-addition gives the trans, and since we only see trans, it must proceed through an anti-addition, which means it must not go through a carbocation. Rather, it's going to go through something called a bromonium ion intermediate, which is a three-membered ring with a positive charge on the bromine atom. So there are three arrows that you're going to use to draw this mechanism for the first step. You draw an arrow from the pi bond to the bromine atom, a second arrow from a lone pair on that same bromine atom to one of the carbons of the alkene, and then you break the bromine-bromine bond, just like this. And then you have what's called the bromonium ion. Then the nucleophile, the bromide that you kicked off in the first step, is going to come in and attack one of the two carbons of the bromonium ion, and then this carbon-bromine bond will break. So the alkene is functioning as the nucleophile, attacking molecular bromine, expelling bromide as the leaving group, and forming this three-membered intermediate called a bromonium ion. Now the bromide attacks from what's called the backside anti to the bromonium ion because that gives the most accessible, less hindered pathway of approach, and as a result you get the trans product, plus it's an enantiomer. So you never get the cis product, you only get the trans product. The second reaction is called the halohydrin reaction, and it involves the use of halogen, again only bromine or chlorine, not iodine or fluorine, in the presence of water. And in this reaction, you again break the pi bond, and you form a new bond to a halogen and a new bond to an OH group. And this is called a halohydrin. Halo for halogen, hydrin for the OH. So the mechanism for the first step is identical to halogenation. You form that bromonium ion. But instead of the bromide attacking and adding in the second step, here water does that. So water will be the nucleophile. So you draw an arrow from a lone pair on water on the oxygen to one of the two carbons of the bromonium ion. And whichever carbon you attack, the bond between that carbon and the positively charged bromide breaks, and the two electrons in that bond form a lone pair on that bromine. So now you get to this molecule, which then will lose a proton in a subsequent step to get to the neutral product. Now the reason that you get the water attacking instead of the bromide is that this is typically run in water as a solvent, so there's just way more water than bromide around, so statistically it's going to be much more likely that a water molecule will collide with the intermediate than another bromide. So here I show the nucleophilic attack on the bromonium ion, and this is followed by a proton transfer. So a second molecule of water is going to grab an H here, break that bond, leaving behind the electrons of that oxygen to get to the trans product where the bromine and the alcohol functional group are trans to each other. And then you'll also get the enantiomer. And if you did this with chlorine instead of bromine, you would get this product. And this would be called a chlorohydrin. This is called a bromohydrin. And then halohydrin is just the generic name. Now a halohydrin is regioselective. The halide adds to the less substituted carbon and the OH group adds to the more substituted carbon. So here are the two carbons of the alkene. The carbon on the right has two H's. The carbon on the left is connected to two carbons. So the carbon on the left is more substituted because it's bonded to two other carbons. The carbon on the right is less substituted because it's only bonded to hydrogens. So the bromine ends up on the less substituted carbon with the two H's, and the OH group ends up on the more substituted carbon. This regioselectivity results from water attacking the more substituted carbon faster than it attacks the less substituted one. So here we see this difference in carbon substitution, and water is going to attack the more substituted carbon of the bromonium. The regioselectivity results from water attacking the more substituted carbon faster than it attacks the less substituted one. And in the transition state, for the step where the water attacks the bromonium ion, the more substituted carbon has more cationic character. In this transition state, this carbon is more electrophilic than this carbon because of that buildup of positive charge. Therefore, the nucleophile, the water, attacks the more electrophilic carbon. You can also use a reagent called NBS, which is shown here, in the presence of water, and dimethyl sulfoxide, which is a solvent, to transform an alkene into a halohydrin. You would use this sometimes because it generates bromine in the flask, rather than having to use bromine as a reagent that you would get off the shelf, which is quite toxic. So this is a safer source of generating bromine in the reaction. Now test your knowledge. What is the intermediate formed when 4-methylcyclohexene reacts with bromine in an appropriate solvent? Put your answers in the chat. Now look at this reaction and determine the product. Based on the mechanisms I showed you for the halogenation and halohydrogen reactions, do you expect to see a carbocation rearrangement in the mechanism? Why or why not? Here's a picture of chlorine gas in a flask. If you reacted chlorine with this alkene, what product or products would you get? There may be more than one correct answer. So in this reaction, first ask yourself, are you going to form a cis product or a trans product? And then ask yourself if you will form enantiomers or diastereomers.